Hi everybody. Many Mechatronics systems can be divided in so-called basic systems. This is video number 2 in a series of 3 videos, and in this video I'm going to discuss second order systems. We start off with a second order system from the electronics. There could also be second order systems from mechanics, for instance a mass spring damper system, but let's start to discuss an RLC network. And in that network we have an input voltage over here, U in, and we have a voltage of the capacitor which is U out. And we want to derive the differential equation. Well, what we could do is to use one of Kirchhoff's laws, and we could say the input voltage equals the voltage over R1 plus the voltage over L1 plus the voltage over C1. So UN is equal to R times I plus L times di dt, which is the voltage across the capacitor, plus my output voltage, which is the voltage over the capacitor, so plus U out. And we want a relationship between U out, U in, and only the parameters R1, L1, and C1. So in this equation, there is an I left, the current. So we have to replace that current by an expression in which the capacitor and the output voltage should be available. Well, we know that I is equal to C times du dt. So C times the derivative of the voltage of the capacitor. And that voltage over the capacitor is U out. So we can replace the I in this formula by C times du out dt. And then we get this formula, LC times the double derivative of U out, well that's this part, L times di dt, L times C times di dt, so the double derivative of U out, plus RC times du out dt, so R times C times the derivative of U out, which is R times the I over here, so replace the I by this expression, plus U out, which is this part of the expression, is U in. And I put it in that way so we can easily see that it's a second order differential equation, because this is the highest power of the derivatives. So I put that to the left side of the equation and then the input to the right side of the equation. So again, Kirchhoff's law, fill in the I, and then you get this expression. Now we can easily transform this into the Laplace transform. It's a Laplace equation by replacing ddt by s, and then we get LC times s squared, d squared divided by d squared t. Well, I shouldn't say that mathematically, but that is what we do. Replace that by s squared, so we get LC times s squared times u out. So LC times s squared times u out, plus RC times, this becomes S times U out, RC times S times U out, plus U out, 1 times U out, equals U in. And now we can define the transfer function U out over U in, which is equal to 1 over LC times S squared plus RC times S plus 1. And also from this equation, we can see that it's a second order transfer function, because S to the power 2 is the highest power of S. So it's a second order transfer function, which was expected because we have a second order differential equation. In a normal form, this is the expression of a second order system. And it says H, in general, H, transfer function of my system, is equal to a constant k times omega 0 squared divided by s squared plus 2 times beta times omega 0 times s plus omega 0 squared. There are 3 parameters which are new, which are our omega 0, the beta, and the k. Well, the k is an easy one. K is just a constant value. It could be a gain, which could be present in your system. The beta, however, is what we call the relative damping factor, and it's a unitless number which says how many the output signal will be damped. The omega 0 is the undamped angular frequency in radians per second. We also call it the natural frequency. And during this presentation, I will present two more values of frequencies, I will introduce the damped angular frequency, which will be omega 0 times the square root of 1 minus b squared. And that is more or less a frequency of a system in which it keeps on oscillating, so to say. And we have a resonance frequency, and the resonant angular frequency is omega 0 times the square root of 1 minus 2 times beta squared. And that's the frequency in which my system wants to resonate, so get really uncontrolled amplitudes. We come to that later. Well, so that's the definition in general of a second order transfer function. Now again, let's look to our system, our RLC system, and we try to compare that with the normal form of a second order system and try to calculate the omega 0 and the beta and the k. Well, this was my transfer function. I discussed it a minute ago. It was equal to 1 over LC s squared plus RC times s plus 1. So now let's compare that to the normal form. What we see here in the denominator is that the gain in front of the s squared in the normal form is 1. There's nothing in front of this s squared. In my expression from the RLC filter, there is a gain over here which is equal to L times C. So in order to make this comparable, I have to put a 1 over here, and I can do that by dividing this part by LC. Then I get LC over LC, which equals 1, which is the one which stands over here. But when I do that, I also have to divide RC over LC. And I should divide 1 over LC, and I should do it with the term in the numerator, so also this part will be 1 over LC. So I get 1 over LC, and in the denominator s squared plus RC divided by LC times s plus 1 over LC, which is equal to 1 over LC divided by s squared plus, this becomes R over L, so get rid of that C, times S plus 1 over LC. And now I can compare this with the normal form. So this is my normal form, and this is the expression for the transfer function of this system. And now I can say 2 times beta times omega 0 should be equal to R over L. And of course, omega 0 squared should be equal to 1 over LC. So when I have this system, I can calculate what the angular frequency, the oscillation, the undamped angular frequency will be, the omega 0. And when I have that omega 0, I can substitute it in this equation, and I can calculate the relative damping factor beta. So let's do it. I have 2 times beta times omega 0 was R over L, and omega 0 squared was 1 over LC. So starting with this one gives us omega 0 is 1 divided by the square root of LC. And of course, when you look to it purely mathematical, then it should be plus or minus 1 over the square root of LC. But we as physics or as engineers, we know that our frequency will only be a real value. So I only take the positive value, 1 over the square root of LC. So I can say beta is R over L divided by 2 times omega 0, or R divided by 2 times L times omega 0. And now I can substitute this value for omega 0 in this equation over here, and then I get R divided by 2 times L times this expression, 1 over the square root 1 over the square root of L times C. Well, I can multiply numerator and denominator with the square root of L times C, and then I get R times the square root of L times C, and here it will be gone, so it's only in the denominator is only left 2 times L. I can make a somewhat more easier expression. I can say, well, that is 0.5 times R times the square root of C over L. So this is my damping factor. Okay, that was purely mathematically. So now let's look to an example with numbers in it. Suppose I have this system. H is the transfer function which is equal to 1 over 2s squared plus 3 times s plus 8. And now I want to calculate, I want to calculate the omega 0 and I want to calculate the beta and I want to calculate the gain k over here. So the first thing I want to do is to get rid of this value 2 over here, because then it says 1 times s squared, which is also the case in normal form. But then I have to divide this part by 2, that part by 2, and the part in the numerator by 2. So then I get 1 over 2 is 0.5 over here, divided by s squared plus 3 over 2 is 1.5 times s plus 8 over 2, which equals 4. So now I know 2 times beta times omega 0 will be equal to 1.5 and omega 0 squared will be equal to 4. So omega 0 will be 2 and 2 times beta times omega 0 is 1.5. So beta is equal to 1.5 divided by 2 times omega 0, which is equal to 1.5 divided by 2 times 2, which is 0.375. Okay, now we can also calculate the k, because I know k times omega 0 squared is the 0.5 over here. Omega 0 squared is 4, so k is 1 over 8. So I have the complete transfer function put in a normal form, and I have calculated the omega 0, the beta, and the k over here. Well, another example, let's say we have this as a transfer function. We do the same thing. We have the 2 over here. We get rid of it by dividing 2 over 2. So we have to divide 24 over 2, which yields 12. And I have 1 over 2, which yields 0.5 over here. And in the numerator, we get 4 over 2, which equals 2. So my transfer function is 2 over s squared plus 12s plus 0.5. So again, 2 times beta times omega 0 has to be equal to 12, and omega 0 squared has to be equal to 0.5. That means that omega 0 is the square root of 0.5, which is 0.707, and my beta will be 12 divided by 2 times omega 0, which is equal to 12 divided by 2 times 0.707, which is equal to 8.49. And k times omega 0 squared is equal to 2. So k is 2 over omega 0 squared, which is 2 divided by 0.5, which is equal to 4. So it's a k over here. So again, I have to put the transfer function in the normal form, and I calculated the omega 0, the beta, and the k over here. So what does that mean? First of all, let's look to the poles, because we are engineers and we want to see what does that mean for our physical system. And we have seen in earlier videos that the poles of my system are really determining how my system will respond. So we are calculating poles of this system. Of course, this system doesn't have any zeros, but because there's no expression with an s in the numerator. And we can calculate the poles of this expression by putting this equation to 0. Then we get the poles, which are equal to, using the ABC formula, minus b, which is this part of the equation, plus or minus the square root of the discriminant divided by 2 times a, which is 2 times 1, which is 2 over here. And the discriminant was b squared minus 4 times a times c, so it's b squared, with it, which is 2 times beta times omega 0 squared, minus 4 times a, which is minus 4 times 1 times c, which is omega 0 squared. So working that out yields this expression. Minus 2 times beta times omega 0 divided by 2 is minus beta times omega 0. And when I put this underneath the square root, it becomes 4. This is 4 times beta squared times omega 0 squared divided by 4 is beta squared times omega 0 squared. And I can put the omega 0 in front of the square root because it's also available over here. So we get in the square root over here, the square root of beta squared minus 4 over 4 is minus 1. So this is the location of my two poles. One pole at minus beta times omega 0, minus omega 0 times times the square root of beta squared minus 1, and the other one has the same real value over here plus this value over here. Okay, so now we see that the determination of the pole, so the position of the poles depends on the value of beta. And why is that? Well, look to this expression. Look what happens over here. When beta is greater than 1, so it's a positive value but higher than 1, then this value is positive. So this square root is a positive value. So then I have here a real value and here a real value, which yields two real values. So I have two poles on the real axis of my system. So two different real poles. When I when beta, the beta of my system is equal to 1, then this expression is 1 minus 1 is 0. So then I have two poles plus or minus 0, so two poles on exactly the same position. So that the poles are equal to minus beta times omega 0. And when beta is smaller than 1, then this expression will be negative, which means that the square root of a negative number will yield a complex number, with this as the real part of the pole, and then this will be the imaginary part of the pole. So then I get two poles with the real part equal to minus beta times omega 0 plus or minus omega 0 times j, because this will become negative. So I get j squared over here, and the square root of j squared is j times the square root of 1 minus beta squared. So in that case, I have two complex poles with the same real value and two opposite imaginary values. So two conjugated poles. So the value of beta, the value of my relative damping constant, is really important. This is what we call the real part of the pole, which has been defined as a lambda, and this has been called the imaginary part, or the damped angular frequency of my pole. So this is my imaginary part of the pole. So my pole is lambda plus j times omega g, what we call the damped angular frequency, also often called as omega. So lambda plus or minus omega. Okay, so we have three situations, and we can define these three situations of beta according to the behavior of my output signal. Suppose I am putting a step signal in my RLC filter over here. So I set a step voltage to the input and I measure the output voltage. What happens according to these three variations of beta? Well, when beta is higher than 1, I see to the output, and I will show it in a couple of minutes, I see to the output that I have a so-called over-damped system. I have a system in which the output voltage in this case will get slowly to the end value. When beta is 1, then my output voltage in this example is so-called critically damped, which means that I have the fastest output signal without any overshoot. And when beta is smaller than 1, my system becomes smaller, but it's called underdamped. There is too less damping, and my output signal will show a kind of oscillation. Well, how does it look like? Well, this is an example. Again, when beta is higher than 1, then I have an overdamped signal response. And the signal output signal could look like this, really slow going to the end value. But it's never be higher than my end value. So I don't have any overshoot. When beta is 1, then my system response is critically damped. So it will become faster, but it will also not cause any overshoot, but it's faster than the overdamped situation. And when beta is smaller than 1, then I have a so-called underdamped signal. I have a faster response, but what you can see over here is that I have so-called overshoot. So at this point, my value is higher than the end value, and then it oscillates and it damps out towards the end value. So it's really depending on the requirements of your system whether or not this behavior is allowed. So again, back to the poles. In a overdamped situation, we've seen that we have two different real poles. Well, an RLC system or a mass spring damper system is a stable system, so my two real poles are on the negative real axis. For instance, over here, one pole here and one pole there. When beta is 1, I have my so-called critical damped system, and my poles are on exactly the same location. For instance, over here. And when beta is smaller than 1, I have my underdamped situation, and I had two complex poles with the same real part but with opposite imaginary parts. So this is the conjugated pole with respect to that one. So often, as always, two poles, but with a real part and an imaginary part. There's one other exemption, which is the situation in beta is 0. And when beta is 0, this part of my denominator, this part of my equation will be 0. So I don't have any damping at all, which is, of course, not valid in a physical system. But when that is the case, and it could be the case, for instance, in a mathematical system, then I have purely oscillations, which means that my poles are equal or can be calculated by putting s squared plus omega 0 squared to 0, which yields two poles on the imaginary axis. So the lambda is 0, and I only have two poles on the imaginary axis, which means that there is purely oscillation and no damping at all. All right, that was about the pole location and the behavior in the time domain. What we have seen is that when we have a high beta value and when we decrease the beta value, my system will become faster and faster, and from a certain point, the beta value smaller than 0, I will get some overshoot over here. And the smaller the beta will be, then the overshoot will be higher and higher. And I have two complex poles at the moment overshoot occurs. Now let's look to the frequency domain with the Bode plot. And in the frequency domain, I replaced S by j omega. So my transfer function is now equal to k times omega 0 squared divided by, this was my S, so it's now j omega squared plus 2 times beta times omega 0 times j omega, this was yes, plus omega 0 squared. In the Bode plot, I have my Bode amplitude plot and my phase plot. And when I look to the amplitude plot, I can calculate my amplitude by taking the absolute value of this transfer function, which is equal to the real number over here, the numerator, divided by the absolute value of the denominator over here. Well, look to this value, j omega squared. When j omega is squared, then I get j squared times omega squared. And j squared is minus 1. So this can be substituted into minus omega squared. So when I take the absolute value, I can take the absolute value of the numerator, which is k times omega 0 squared. And I have to divide it by the square root of the real part squared plus the imaginary part squared. Well, the real part squared is omega 0 squared, and this is minus omega squared, and that part squared. The imaginary part is 2 times beta times omega 0 times omega, and that's squared. And I have to take the square root out of it. Well, it's a second order system. First of all, let's look for real low values of omega. Well, we can see it directly from my transfer function. When omega is, for instance, 0, then this these two parts are more or less gone, so I have k times omega 0 squared divided by omega 0 squared, which is k, and when k is 1, I start off with 0 dB over here. That's what we can see over here. Um, from a certain point, which is almost my omega 0, almost this frequency over here, my low end frequency behavior is replaced by my high frequency behavior. And what we have seen for the first order system, that the decay is always minus 20 dB per decade for a first order system. Well, this is a second order system, so my decay is over here minus 40 dB per decade. And remember, a decade is multiplication of my frequency by a factor of 10. So it ends up with minus 40 dB per decade. What's in between at this resonance frequency is really depending on the value of beta. And you can see it over here. When beta is very small, the amplitude around the resonance frequency will get very high. So because when beta is very small, the denominator gets small, and this expression will be ending up with a high value. The higher the damping will be, the smaller this expression will be. So that is what we see over here. The smaller the beta will be, the higher this peak will be. And that occurs from a so-called resonance angular frequency, omega r, and you can calculate that by multiplying omega 0 by the square root of 1 minus 2 times beta squared. So for very small values of beta, it's almost at omega 0 when this behavior occurs. So at a beta value of the square root of zero point 0.5, so at 0.707 beta is 0.707 or smaller, then resonance in the frequency domain occurs, what we can see over here. So at really small values we get really high peaks over here, so we have a really we have a resonance frequency in which your system, for instance your Mars spring damping system, can really yield very high amplitude when it's operating at that resonance frequency. So you have to take care of that. Well, looking to the phase diagram, we have seen for first order system that it starts off with 0 dB for low frequencies, and for higher frequencies it ends up at minus 90 degrees. But this is a second order system, so it ends up at minus 180 degrees. And depending on the value of beta, you see how this phase characteristic goes from the low frequency part to the high frequency part. And the lower the beta value is, the more abrupt this behavior will be. Well, that's about what we call the resonance angular frequency, and also around that frequency we have our definition of the bandwidth, which is often equal to the undamped angular frequency omega 0 over here. Well, does it occur in real life? Yes, it occurs. Well, you could do an experiment by yourself by a spring and a Mars connected to it. When you move it at a certain frequency, you can see that this starts to behave with real high amplitudes. And of course, in an electromechanical system or in a drive system, this spring could be a belt, for instance, in a printing system with a belt, and that carriage on which the printheads in this example have been mounted, that could be my mass. So you have to take into account that there is a resonance frequency. So when you design that system, you have to take that into account. Okay, now back to the time domain. We have seen that this is my expression for a transfer function in the S domain. And of course, we have requirements in the frequency domain with the Bode plots, etc., and the S domain with the position of my poles. But of course, we have also requirements in the time domain, because your system has to function in the time domain. And the first requirement or definition of a parameter you should take into account is the so-called overshoot. And the overshoot is defined as the maximum value of your output signal minus the static value, the end value of your output system, and that divided by that end value, that static value of that output signal, so you get a relative number over here. So when you have a measurement of a second order system with some oscillation over here, so with a beta value which is smaller than 1, you can measure the overshoot, which is equal to y max minus y stat divided by y stat over here, and often times 100% when we define it in percentages. Um, you can also calculate that maximum overshoot when you apply a step to the input, and you can calculate it by um, using the exponential harmonic signal definition, and then you can see that the maximum overshoot is equal to e to the power minus the absolute value of lambda over omega times p. So remember, lambda is the real value of the pole and omega is the imaginary value of the pole. So when you know the pole locations, then you also can predict what the maximum overshoot will be, because, as I said, it's equal to e to the power, the absolute value of the real part of the pole divided by the imaginary part of the pole with a minus and multiplied with p. Well, you know that lambda is equal to minus beta times omega 0, and omega is omega 0 times the square root of 1 minus beta squared, so you can also get an expression with the beta in it. So again, when you know beta, and you don't have any measurements, but you know the beta of your system, also then you can calculate and predict what the maximum overshoot will be when you apply a step signal to the input. So that's very nice. Then we have another definition, and that is the peak time. And the peak time is the time at which the maximum overshoot occurs. And you can define it by and calculate it by dividing p over omega. So p divided by the omega, which is the imaginary part of your pole. And when you know that, you can also substitute it by omega 0 times the square root of 1 minus beta squared. So again, then you can calculate based on the parameters which you have of your system, you can calculate at what time the overshoot will occur. And of course, when you put a step to the input. Then we have the rise time of your output signal, which is the time between 90% of the end value, of the static state value, which I should say, minus 10% of the end value of the system. So that's the time between 10% and 19% of the final value. And another parameter which is often used when a system is defined is the so-called settling time. And there are two settling times. First of all, the definition of the settling time is the time that it takes before this signal is within a so-called band around the end value. We define two settling times. The first settling time is the response time, and that is what we call the time in which the end signal stays within 5% of its final value. So you can see it over here. These two red lines define a band around the output signal of 5%. And you see the oops over here, the signal stays within 5% of its end value. So you can say, well, the response time is this time, the time between that value, that the output signal is within 5% of its end value related to the start of your output signal. There is also another one, which is the indication time, which is the time in which a signal stays within 2% of its final final value. And of course, that indication time is higher than the response time. Well, why have they defined the response time and the indication time? That is because you can easily calculate also the response time and indication time. Well, when you know the expression from the exponential harmonic signal, you can calculate the response time, so the 5% settling time by dividing minus 3 over the lambda, which is the real part of your pole, so which is equal to beta times omega 0. So again, when you know the pole location, then you can calculate the response time, the 5% settling time, which is response time. So you know how long it takes before the oscillation ends. And you can also calculate the indication time, because that indication time is minus 4 over lambda. So minus 4 over the absolute value of um, of my pole, so the real part of my pole. So minus 4 over lambda. So minus 4 over the real part of my pole. So again, when you know the location of the poles, you can calculate the overshoot, and you can calculate the settling time, and you can calculate the peak time at which the overshoot occurs. Well, I know that was a lot of information about the second order system, but it's a system which is often used in control system and in mechatronic systems. Well, I hope yeah, you more or less enjoyed the video and studied the video. So I hope to see you again in a new video. Bye bye, and thank you for watching.